recording. So, do either of y'all have any questions before we get started?
Maybe at the end or after we do what we were going to do today, can we go over a titration problem again?
Sure. Yeah, as long as we have time, sure.
Okay.
We can absolutely do it. And then, yeah, okay. I might have to go. I mean, I could definitely do a titration. I might have to do it quickly. Just depending on how long it takes us to get through. Kind of, there was a request to do the review for the test today, so I am going to do a review for this today. Okay, well, let's go ahead and get started then. If there are any questions, of course, please stop me at any point. On this test that we will be having a week from today, or from yesterday, is what I'm saying, we will be having the modules 6 and 7. So we're looking at our acid-base equilibrium chapter, and then we are also looking at our KSP chapter, or our solubility product chapter. So some things, I'm just going to kind of go through some things for the actual in-class portion today. Just, so we know what kind of concepts we should be expecting. I'll just very briefly go over them, although if at any point you guys want me to delve further into any of them, please let me know. So first, with acid-base equilibrium. When we look at this chapter, or this module, or whatever you want to call it, we generally look at our acids and bases in one of two ways. We either look at our acids or our substances when we throw them into water, or what they do when we interact them with another thing. So an acid with a base, or a base with an acid. So if we have an acid plus water, so if we're just seeing what happens as we throw an acid in water, there's going to be different reactions based on whether it is a strong acid or a weak acid. So if we have a strong acid in water, and I'm going to call that strong acid HA subscript S for strong. So we have our HA, add water to it. We're going to have a one-way arrow producing hydronium and our anion from this process. Okay. In this case, if we're dealing with a monoprotic acid, and with the exception of H2S, or H2SO4 rather, all of our strong acids will be monoprotic. The HAS concentration will be equivalent to our H3O plus concentration. And then our strong base in water. And this is going to be some BOH X complex. So with this, I don't really show the water because the water would cancel out, because the hydroxide itself does not attach onto the water like the hydrogen from an acid does to produce hydronium. So when we have this BOHX, it's going to break down into our ions, so our cation and our anion hydroxide. Here, our BOH concentration will be equivalent to X, or well, I guess concentration of hydroxide. Well, yeah, no, I said that right there. So. Sorry, 1 second. Sorry. We'll put the X over on this side. A hydroxide concentration, whatever that X is, whatever the magnitude of charge or the number of hydroxides, we would solve for a hydroxide concentration by multiplying our base concentration times by that X. When we're dealing with a weak acid in water, weak acid, it will, and we're going to call this HAW, W for weak. When it reacts with water, it will partially hydrolyze. And then there'll be some amount that is going to be in solution. So to determine our H3O plus concentration, we have to take our Ka. So keep in mind that our Ka will be equal to our hydronium concentration times by our anion divided by our intact molecule. So we could solve for a hydronium concentration by essentially taking our Ka now we could rearrange that equation, but usually we would say that this would be equivalent to the X that we solve for using a Rice table and the equilibrium expression. Equilibrium expression. Okay. Lastly, we have a weak base in water, which we're just going to call B for base. That base will react with the water, removing a hydrogen from the water and producing hydroxide in the process. So again, with this one, here we're going to have a Kb. That Kb will be equal to our conjugate hydroxide concentration and our B concentration, all at equilibrium. And we could say the same thing that we did over here. It's gonna be lazy and so here our hydroxide concentration will be equivalent to our Kb times by our B divided by OH minus, not OH minus, let's try that again. BH plus. And it's also equivalent to the X that we solve for in here. Neither of these cases are we really looking at a polyprotic or a polybasic substances. So just one simple Rice table will do for these. Now, as a note, we will not be doing any of this math in the in-class portion, but you should know what's going on conceptually with all of this. Okay. So another thing we're going to look at is our acid-base theories. One of the other things we looked at, I guess, would be acid-base theories. So we looked at our Arrhenius definition or theory. Here, an acid produces H plus or H3O plus in water, or we could say that it increases the concentration of H plus or H3O plus in water. Okay. And then our base produces OH minus in water. Again, we can also just say that it increases the hydroxide concentration in water. Either one will work. Not really sure what that ended up being. Okay. That's our Arrhenius definition. We have our Bronsted-Lowry. So an acid is going to be a proton donor. A base is going to be a proton acceptor. So very simple definitions for those. And then Lewis, an acid is an electron acceptor. And then a base is an electron donor. Okay, you should be able to draw out the Lewis structures for our acids and our bases. That could be expected on an exam, and show where hydrogens are going, show where electron pairs are going, and identify if a substance is an acid or a base, and by what definitions. You should also be able to come up with all of these definitions. Okay. You should know what the KW is. So the equilibrium constant for water, or the dissociation of water. So if you have two water molecules together, they're going to react to produce hydroxide and hydronium. And we have a set concentration of hydroxide and hydronium based on our KW, where KW is equal to 1 times 10 to the negative 14 when we were at 25 degrees Celsius. If we change that value, we can change our KW as a note. Remember, temperature is one of those things that if we change it, we can change our equilibrium constant value. You should be able to identify and come up with or draw a conjugate acid-base pair. Keeping in mind that a conjugate acid-base pair is going to be, that is part of the Bronsted-Lowry definition. But you should know that we talk about an acid and its conjugate, it'd look like that. If we're thinking about a base and its conjugate, it would look like that. Generally, I don't know, I was gonna go with that. Come on. So it's just your conjugate acid-base pairs are going to be 1 proton difference between the two. you need to know which acids and bases are strong. So you need to know that list of acids and the bases. You should also be able to determine the strength of the conjugate based on the other substance. I guess specifically, let me actually write this in a different way. The conjugate base using the strength of the acid and vice versa. So we know if we have a strong acid, we're going to have a very weak conjugate base. Generally, we consider this to be non-basic if it's a strong acid. And then if we're thinking about a weak acid, it's going to have a weak conjugate base. And if we have a weak acid and a weak base, Ka times by Kb is equal to Kw for those species. You should know that a low pH is acidic. A high pH is basic. And additionally, a high pOH is acidic. Low pOH is basic. We also talked about comparing acid strength. So looking at two acids and determining which one is stronger. As a note, whichever one's stronger, that one will have the weaker conjugate. So that is something else to keep in mind. But if we're talking about a binary acid, HA, we're looking at the bond between that proton and that anion. The weaker that bond, the easier it is to break that bond, and therefore the easier it is for us to accumulate a larger amount of H+ ions. So a weaker bond results in a stronger acid, because our acid strength is based on how many protons per mole of acid we produce. So we can decrease our bond strength by increasing our electronegativity of A. So larger, specifically if we are in the same period, the electronegativity of A, as we increase the electronegativity of A, we're going to decrease the HA bond strength, and we're going to increase the acid strength. If we are in the same group, if we increase the size of A, we're going to decrease the HA bond strength. And that's going to cause us to have an increase in our acid strength. If we are talking about a oxyacid, we have HAOX, right? Wow, yeah, HAOX. So if we are looking at the same number of oxygens, so same X value, as you increase the electronegativity of your A, you're going to pull electron density away from the oxygen and then the hydrogen. So I'm just going to go away from the hydrogen. And that's going to result in a weaker or smaller, weaker OH bond strength, which will result in a greater acid strength. Okay. And then H, well, if we have same A, different number of oxygens, greater number of oxygens will result in greater number of resonance structures for the conjugate base. When we have a greater number of resonance structures for our conjugate base, that's going to increase the stability of the conjugate base. Increased stability is going to mean it's going to be a favored substance. So this is going to cause us to increase our acid strength. So if we have HNO3 versus HNO2, we can say right away that HNO3 is the stronger acid, but the reason is because when it loses that proton, sorry, is it? We have a couple of different resonance structures that we can have for this. We can have this one. Or that double bond can go around the structure. So there are 3 resonance structures. With our conjugate here, we only have 2 possible resonance structures for this. And as such, it's going to be less stable. Okay. Keep it on, keep it on. What if this is just salts. So salts, this is the product of an acid base neutralization reaction. So up top, like all until this point, kind of, we've been looking at just throwing these acids and bases in water. Now we're going to look at adding an acid to a base or base to an acid. The most common is going to be the most common base is a hydroxide base for these neutralization reactions. So we can have HA plus BOH goes to H2O plus Ba. So this is a salt that we're talking about. But we can also have a salt made from, if we have so this is a hydroxide base. Neutralization reaction, we can also have a carbonate base neutralization reaction. So HA plus Na2CO3. So this would produce CO2 plus H2O plus NaA. Nope, one, just kidding. And then this would be our salt. Then we also have a amine base. So we have our acid and then our amine base. And what happens is we produce, in this case, we will produce a Lewis addict, but this is still a salt. So it's salt, salt, salt. As a note, to be a neutralization reaction, either the acid or base must be strong. You can have them both be strong or just one of them. But another note, carbonate bases and amine bases are weak bases. So if we do a neutralization reaction with either one of these, we have to have a strong acid. So with all of these neutralization reactions, we see that we have one-way arrows. We will not have equilibriums with these neutralization reactions. Okay, our salt can be acidic, basic, or neutral. Keeping in mind that the conjugate of a strong acid or a strong base is a very, very weak conjugate base or conjugate acid. We essentially consider them to be non-acidic or non-basic or neutral. So if we have a strong acid, its conjugate will be a neutral anion. If they have a strong base, its conjugate will be a neutral cation. If we have a weak acid conjugates a weak base, so it would be a basic anion. And then a weak base has an acidic cation. So neutral plus neutral. This is a neutral salt. Neutral plus basic would be a basic salt. Neutral plus acidic, acidic salt. Basic plus acidic. This is going to be dependent upon Ka and Kb. This, as a note, would not be formed during a neutralization reaction. We can take an acid and a base, react them together that are both weak, but we don't consider that to be a neutralization reaction. This is a weak acid plus weak base. So not a neutralization reaction. But we can still determine the acidity or basicity of the salt according to which substance is stronger, your acid or your base. So if we think about it, your strong acid will produce a neutral base. So a stronger acid will produce a weaker base. Versus a weaker acid. As a result, you're going to base, again, Ka and Kb. That'll determine if you have an acidic or a basic salt. So in the case that your Ka is greater than your Kb, that means you have a stronger acid, a weaker base, which makes, stronger acid, weaker base. This stronger acid will make a weaker conjugate base. The weaker base will make a stronger conjugate acid. And what we get is a salt that is acidic. So we can look at it in terms of the conjugates themselves. Since a stronger acid has a weaker conjugate, it would result in it being less basic than acidic, which is an acidic salt. You can also just look at it, this way. Ka is larger than Kb. We have an acidic salt. And then, of course, the other way would be true as well. If Ka is less than Kb, then we have a basic salt. You guys should also be able to draw Lewis acid base, the Lewis adducts. So something like we have NH3 along with BF3. In this case, our atom on the left, the central atom, is more electronegative and it has a pair of electrons. So it is going to be our electron donor. On the right side, our central atom has it's lacking an octet. So it is electron deficient. So this is going to be an electron acceptor. And usually finding which one the electron acceptor is a little bit easier because on the right molecule, BF3, we have 3 atoms with electrons. So it's a little bit harder to distinguish which one will be your electron donor. But your electron acceptor is going to be the thing that is electron deficient. Usually has a partial positive charge. So I would go with looking for, with the Lewis acid base theory, I would look for the species that is electron deficient. And then from there, you can determine which one is your acid and your base. So electron donor, that is a base. An electron acceptor is an acid. And then the way that this would work is this electron pair on this electronegative atom is going to go towards this positive. Because it's already electron deficient and it has less than an octet, we do not need to break any bonds, right? We will not be beyond an octet when we make this, so we're good. As a note, the electron donor will become more positive after this reaction. The electron acceptor will become more negative after this. And we actually see that if we do our formal charges, you would have a +1 formal charge on your nitrogen and a -1 formal charge on your boron. That's interesting. Sorry. Let's look at OH minus and I don't know, whatever species this is. Looking at this, I don't know, I just kind of made something up. So in this case, we see which one our positive center is. It's lacking, or it has a multiple bond, which means it's electron deficient. It also has a positive charge. In this case, we'd come here, kick that off, and then that would make us have more than 4 bonds to that phosphorus. So we'd take this electron pair and go up that direction. When we did that, we get negative charge there. That right there. That right there, and then that right there, which would have a resonance form. Like so. Right. And that is at base equilibrium. I'm sure I'm forgetting something, but that's all I can think of right now. Any questions about any of this? When you have time, could you go over number 38 for module 6 on Chem 101? I can go over that as soon as we get done with this. Okay, so let's keep on. If there are no other questions, we'll go ahead and go over the last module. This one should not take very long. So first, we have the common ion effect. It's the idea that if you add, or you combine a solution containing a strong electrolyte with a weak electrolyte, a solution containing a weak electrolyte, or something whose solubility is described by an equilibrium process. And they share a common ion. You will decrease the ionization of the weak electrolyte, or of course, is something, so the equilibrium substance. We can look at this for a weak acid. Or we can look at this for a slightly soluble or insoluble salt. So either one of these are considered equilibrium processes. So I'm going to change this real quick. Sorry.
Oh, not 3. What am I doing? Oh, my brain really has gone. Carbonate. There we go. If we add in a strong electrolyte to either one of these solutions and they have the same ion, doesn't matter what kind of ion. So this could be, for this one, it could be an acid, a strong acid, or it can be like sodium fluoride. For this one, it could be really just a strong electrolyte that has either calcium or carbonate that completely dissolves. This would cause us to dissociate less. If we dissociate less, this will be less acidic. If this dissociates less, this is going to be less soluble. With buffers, you should know the buffer capacity. You should know the buffer range. And you should be able to describe how to make one. Keeping in mind that your buffer is going to be a weak acid in its conjugate base or a weak base in its conjugate acid. And you can make a buffer either by just adding those two substances together, or you can also make a buffer by taking a weak acid and partially neutralizing it with a strong base, or taking a weak base and partially neutralizing it with a strong acid. So something like that. And then we have a weak base plus its conjugate acid. Always hard to remember weak bases. I guess something like NH3 and NH4Cl. Or partial neutralization. Of a weak acid by strong base. So we could take acetic acid plus sodium hydroxide. We would produce sodium acetate and water. And what we want is something like 1.00 moles here and 0.50 moles here. So we want our strong substance to be limiting. Or partial neutralization of a weak base by strong acid. So NH3 plus HCl goes to NH4Cl. So again, we want to have our strong substance be in limiting amounts. Okay. You should be able to, for acid-base titrations, you should know the approximate pH at neutralization. You should be able to draw and identify pH curves for strong, strong, or strong, weak, or polyprotic titrations. And you should, know the general procedure of a titration. So you should be able to describe what's going on. Within a titration experiment. You should know what a indicator is. And you should know what kind of indicator you need for a particular titration. We specifically talked about phenolphthalein. I can't spell phenolphthalein. Phenolphthalein. This is for a basic neutralization, or sorry, I should probably actually go with equivalence. A basic equivalence pH. And then we also talked about methyl red. And this would be for an acidic equivalence pH. Let's see. You should also know about the formation of complex ions and what that does to solubility. You should know what amphoterism is. So the idea that a substance can be more soluble in both acid and base versus pure water. And we're going to talk about this on Tuesday, but you should be able to make a general schematic for the separation of ions in solution. Okay. Any questions? Okay. I'm going to go very quickly through a titration.
It's okay. You can do number 36 from the homework.
Well, he's not here anymore.
Oh. Okay.
Okay, but I'm not, again, I'm not gonna do nothing like significant with this, just, like 1 or 2 points.
Okay.
So let's take a titration where we have 45.0 milliliters of 0.100 molar NaOH. So this is our titrant. And then we have 50.0 milliliters of 0.100 molar CH3COOH, which has a Ka equal to 1.8 times 10 to the negative 5. So we're going to look at what happens at this point in our titration. And it's just because I have an example of this and it shows a couple of different things. Okay, so since we have equal concentrations here, and we have less of our titrant than our analyte, we know that our titrant is in limiting amounts. So when we know that we are in the buffering region of our titration. So we are going to, since the partial neutralization, we're going to do a BCA table, and then we can put it into our Henderson-Hasselbalch. So we've got 0.0450 liters times by 0.100 molar NaOH. And this would give us 0.00450 moles of NaOH. And then 0.0500 liters, 0.100 molar CH3COOH, giving us 0.00500 moles of CH3COOH. Set up our BCA table. CH3COOH plus NaOH.
Why did you put them into moles?
Because we're doing a BCA table. And then we have our salt. And anytime you have a partial neutralization, you're going to use a BCA table, so you need to put it into moles. And water. Have 0.00500, 0.00450, are limiting, so minus 0.00450 minus 0.00450 plus 0.00450. Okay. So this ratio is less than 1 to 10. So we're good. If we were to take 0.00450 divided by 0.00050, we get 9 to 1. So that is still within our buffering range. Sorry, buffering capacity. No, buffering range is the first time. So we can use Henderson-Hasselbalch. So our pH will equal pKa plus log We're gonna have our base over our acid. And because they're both in the same volume, we could just put in moles instead of molarity. This is acetic acid, so it's pKa. Would be equal to 4.74. And this gives us a pH equal 5.69. So this is one of the more difficult places within a titration, which is why I wanted to point it out. The other one is probably actual equivalence. So add equivalence. Again, because these concentrations are the same, when their volumes are the same, we're at equivalence. So when we have 50.0 milliliters of NaOH and 50.0 milliliters of acetic acid, both at 0.100 molar, then we are at equivalence. So at that point, we've already figured out our moles of our acetic acid. So our moles of our acetic acid, 0.00500 moles. And if we were to run through a BCA table, so I'll just write it real quick. So running through this BCA table, we're putting these mole amounts in. Do minus 0.00500 and then plus 0.00500. We have a 0 here, and a 0.00500 here. So we can see from this that we're going to convert all of our acetic acid and sodium hydroxide into sodium acetate. So that's all we have at our point of neutralization. So this can then go into a Rice table after we convert it from moles into molarity. We know that we have a total of 100 milliliters. So we can take our 0.00500 moles divided by 0.1000 liters, giving us 0.0500 molar sodium acetate. And then we can go through our dissociation here to see how much of everything we have. So our sodium acetate plus water will produce OH minus, and I'm actually going to get rid of the sodium ion just for simplicity's sake. Like so. This Kb will be equal to Kw divided by Ka, which means our Kb would be equal to, I think it's 5.6 times 10 to the negative 10. So starting out at 0.0500 minus x plus x plus x, 0.0500 minus x, xx, and then put it into our KB expression, 5.8, or sorry, 5.6 times 10 to the negative 10 is equal to x squared divided by 0.0500 minus x. We can do a small x approximation. And then when we do that, we get an x value equal to 5.3 times 10 to the negative 6, which is equivalent to our hydroxide concentration. So we do POH is equal to negative log 5.3 times 10 to the negative 6. Giving us a POH equal to 5.3 and a pH equal to 8.7. Okay, I do have to go. As I have a class in just a few minutes. But did you have any last minute questions before I head up?
No, this is good. Thank you.
Wonderful. Have a great weekend.
Thank you, you too.
Bye.